Okay, so I've got a problem up here on the board. I want to integrate over r, where r is this diamond here, x squared minus y squared with respect to area in the xy plane. Okay. Now, I'm going to do this by doing a change of variables. Okay. This problem isn't atrocious. This region isn't horrible. If I wanted to do this without doing a change of variables, I'd just have to break it up into two pieces. I could do the left side, where this is the bottom to the top, and then the right side, this is bottom to top. Or I could do the bottom, where this is left to right, and top, where this is left to right. The problem is just that I don't have a consistent bottom function or a consistent top function. They change. Okay. So I'm hoping to get some nicer region. This was in the xy plane. I'm hoping there's some nice region in the uv plane that I can map to that. Okay. So the key is this diamond here is a parallelogram. Notice that this is just the line y equals x. This line that goes from -1 to 1 to 0, 2 also has a slope of 1. So this is just y equals x plus 2. Okay. If I have those, anytime I have parallel lines, that essentially means that if I were to subtract this over, y minus x would equal 0. And here, this just means y minus x is equal to 2. So y minus x is constant here. So let's let that be u. Let's let u equal y minus x. Then u is going to go from 0 to 2. Okay. Okay, I'm liking this. If I look at this, this is a line of slope -1, and it passes through the origin, so that's just y equals -x. This is also a line of slope -1. This is y equals -x, -x plus 2. But that means that y plus x here is equal to 0, and here y plus x is equal to 2. So y plus x is constant. Let's let that be v. And then v is going to vary from 0 to 2. So I've got, these are my boundaries. This right here, this lovely square, is my region S. Okay. So that's the region over which I'm going to integrate. Okay. So I've got this relationship between x and y and u and v. Okay. Now, that's actually fairly helpful for me in rewriting the integrand, because I'm going to say now this is the double integral over S. I'm going to rewrite my integrand, introduce my scaling factor, and then say I'm integrating with respect to area in the uv plane. Okay. Now, to find this, I need to express x squared minus y squared in terms of u and v. But if I happen to notice that's a difference of 2 squares, so that's x plus y times x minus y, that's awfully nice, because that's just the opposite of u times v. Now do be careful, it is the opposite of u times v, because I'm getting x minus y, and we define u to be y minus x. Okay. But that way I can rewrite my integrand there. Now, here I need to put the absolute value of the Jacobian. And the Jacobian is the partial of x and y with respect to u and v. Remember, even though I was given the problem here and I'm trying to go back to integrate in terms of s, I'm thinking of that as going backwards. My transformation takes me from s to r. So I'm viewing x and y as the outputs, not the inputs. So these are basically the component functions for the inverse function that takes me from xy back to uv. I need the components for the original function that take me from uv to xy. Now, in the homework, you will explore a fact that says that I could work with the Jacobian for this transformation, for the inverse transformation instead. I just have to make some adjustments. This is a big enough section that I'm not going to cover that in class. But if you work through the homework and you see how you can work with the Jacobian for the inverse transformation instead, you're more than welcome to do that. And I'm happy to answer questions about that in office hours, but I'm just going to show you how to actually get this thing. Okay, so that means I need to get x and y in terms of u and v. So notice we had u equals y minus x, v equals y plus x. I'm just noticing if I add those equations, u plus v is going to equal 2y. So y is u plus v over 2. So I'm able to get y in terms of u and v. Once I have that, I should be able to plug into either of these equations in order to solve for x. I think I'm just going to use this equation and say that, actually, I'm going to use this equation and say that x is just v minus y. So that's going to be 2v over 2 minus u plus v over 2. Okay, so that's 2v minus u minus v. Don't forget to distribute that negative over 2. So that's just v minus u over 2. Okay. So I've got x is v minus u over 2, which is just v over 2 minus u over 2. And y is u plus v over 2, which is u over 2 plus v over 2, if I distribute that division. Okay. So what I want to put here is the absolute value of the determinant of a matrix. Actually, I think I want to do a little bit more side work here. Okay. The matrix whose determinant I want to take is going to be the partial of x with respect to u, partial of y with respect to u, partial of x with respect to v, partial of y with respect to v. And I might get the right determinant even if I mix up the order, but I am going to be checking that you're putting things in the right order, because in other contexts it does matter that you have the right matrix. Okay. All right, that would be the determinant, and I'm going to have to remember to take the absolute value still. Okay. Partial of x with respect to u is negative 1/2. Partial of x with respect to v is just 1/2. Partial of y with respect to u is 1/2. Partial of v with respect to partial of y with respect to v, is 1/2. This is going to be negative 1/4 minus 1/4. That's negative 1/2. That's the determinant. My scaling factor is the absolute value of that, which is going to make it positive. Very, very important that that become positive. Okay, so let's see what this gives us. Notice we did introduce this scaling factor, but the scaling factor in this case ended up being constant. So we actually ended up with a simpler region, and I think a simpler integrand as well. Okay. Okay, so this is just 1/2. I'm going to factor that out and factor out that negative. So I'm going to have negative 1/2. S was just this rectangle, 0 to 2, 0 to 2, uv, it doesn't matter, du, dv. So, negative 1/2, integral from 0 to 2. If I take my antiderivative with respect to u, I'm going to get u squared over 2 times v. We're evaluating as u varies from 2 to 0, and then we'll still integrate dv. So, let's see. That's going to give me 1/2, the integral from 0 to 2. When I plug in 2, I'm going to get 4/2, or just 2v, minus when I plug in 0, I just get 0. Okay. So we're integrating 2v dv. I'm going to cancel that 1/2 with that 2, so we've just got the integral from 0 to 2 of v dv. That's v squared over 2. Did I drop a negative somewhere? I did. There was a negative 1/2 here, and when I copied it up here, I dropped that negative. So this should be negative v squared over 2, evaluated between 2 and 0. Okay. And let's see, so that's going to be negative 4 over 2 is 2, minus 0 is just 0. So we're getting negative 2. Note that's a signed volume. It does end up being negative. That makes some sense because we're getting x squared minus y squared here, and my y's are ultimately going to be bigger than the x's. I can also see I've got some symmetry here. So the x squareds and the x squareds, I don't know that the symmetry helps me. Never mind. I do end up with something negative. That's okay because we were integrating this function, which is sometimes negative. The y values go all the way up to 2. The x values are just between -1 and 1. So not super surprising that we got something negative.